Alright, this video is important, and I will try to keep it as brief and efficiently spoken as possible. This is our derivation of the kinematic equations for uniformly accelerated motion. Remember, all of our motion in this kinematic study we're doing is of uniform or constant acceleration. I'm going to put some what I think are helpful links to the derivations for these equations in the links description of the video. So first I'm starting with my velocity time graph. On my y-axis I have velocity. I've put a bracket around the symbol, which is not usual. Usually we just have the symbol or the name, but I'm putting a bracket around the symbol so you remember, and then in parentheses I have the units meters per second. On the x-axis I have time, bracket, little t there for its symbol, and in parentheses s for second. I've indicated my function with a purple line. It is linear, and that means my velocity is increasing at a steady rate, meaning my acceleration is uniform, it's constant. You can see my velocity is increasing in the positive direction. That means my object should be moving in the positive direction. I should have an upwards curving position time graph, and I also must have a positive constant acceleration. You can see that I have labeled V0, or let's start with the origin. I have an origin down there of x position red 0, y position blue 0. That's my origin 0, 0 down there. I have a t sub 0 or t0 or t0 down there at the very beginning of my x-axis where x equals 0, and a t final over there on the right side somewhere, and in between I call that delta t, or change in t, change in time. And then I have those two positions I've marked as v sub 0, v0, v0 as the beginning velocity, which has some positive value, and then I have some final velocity value up there at the very top. And now I've labeled it a velocity versus time graph. The first equation we're going to look at is the equation that comes from the slope of this line. My slope, as we said before in the previous video, is the change in what's on the y-axis over the change in what's on the x-axis, and that's delta v over delta t, which is our definition for acceleration. We can rewrite this as v minus v0 over t, and as you can see how I've rewritten it, I have a times t equals v minus v0. That's just rearranging the literal equation. At plus v0 equals v, and the way you see it on your AP1 Physics 1 equation sheet is going to be v equals v0 plus at, or final velocity, and this is the one in the orange box, final velocity equals initial velocity plus acceleration times time. On the AP equation sheet, it has little x's by those v's, so that's just to tell you that velocity as a function of time for some position x is equal to the initial velocity as a function of time based on some particle or position x plus the acceleration times the time. You don't really have to worry about those little x's down there. Those are just extra subscripts to be super specific, because sometimes people learn the stuff with different kind of conventions and symbols. But in English, it says the final velocity of an object is equal to the initial velocity of the object plus the acceleration of the object times the amount of time it experiences that acceleration. The second kinematic equation that I'm going to introduce to you is from the area under this curve. And remember, a curve can be just a straight line. So look, we have a triangle and a rectangle, and I'm going to kind of define what the sides of those two objects are in terms of my variables I got up there. So I have the triangle up there. You see the area of the triangle is 1/2 base times height, and I look at what those bases, the base and the height, are, and I have delta t as the base of my triangle, and my height is v minus v0 because it's that space in between. So if my area of my triangle is 1/2 delta t, or the change in time, times delta v, the change in the velocity. That's my height. Also, I have that rectangle at the bottom, and it forms the bottom portion of the area under my curve, and the area of that rectangle is, of course, length times the width, and the length is delta t, or v0, doesn't matter, it's commutative, but v0 times delta t gives me the area of that rectangle. Whatever is on the length on the x times the height of my rectangle, which is v0 minus 0, which is v0. I can write that out, and because like in the last video I indicated and showed how the area under the curve on the velocity time graph is equivalent to the change in position, I know that that area is equal to delta x, or the change in position. And it's also equal to the area of those two geometric objects I just indicated to you and gave the area of in terms of my variables. So the area of the triangle is 1/2 delta v times delta t, plus the area of the rectangle, which is v0 times delta t, and I get delta x, the area underneath the whole entire curve, which is the displacement. If we clean this up a little bit, I end up with the area is equal to 1/2 times something delta v that I'm going to substitute in for that, times the change in time plus the initial velocity times the change in time, which equals our displacement. So see what I've underlined in red in 3 places, the open parentheses, that delta V, and then my V minus V naught up at the top there for my first equation. Yeah, that V minus V naught, that's delta V. And delta V is also equal to acceleration times time. So guess what? That's what's going to get substituted into those parentheses. There they go. And we simplify and we get 1/2 AT squared plus V naught T equals delta X. Delta X is also written as X minus X naught, so add X naught to both sides, and there you go. Boxed orange equation is what you see on your AP equations sheet. Be mindful that delta X is a displacement vector. It could be positive or negative. That V naught is a velocity vector. It could be positive or negative. And that A is a vector. It could be positive or negative, which means if it's negative, it's going to turn into V naught T minus 1/2 AT squared. So just be mindful of the signs. The third equation that we're going to look at, I believe, is and that was a parabolic equation that we just saw, or quadratic, previous one, number 2. So we actually probably saw that in one of our little literal equation videos as well. The next equation we're going to look at is the other area equation that for some reason they don't really teach anybody anymore. But it's a little simpler. I could also find the area under this curve, or straight line in this case, just by finding the area of a trapezoid, because that's actually what this thing is, a triangle with the rectangle. So the area of my trapezoid is defined as 1/2 base 1 plus base 2, all of that times the height. So I can define my height there as delta T, that's the height, and the bases are the two ends, 0 to V naught on the left, and then 0 to V final on the right side of my trapezoid. And all of that, again, is going to equal the displacement because it's the area under this curve. So there I'm dividing my base 1 and base 2, and when I write it out, the area of my trapezoid is 1/2 V plus V naught times T equals delta X, or delta X, the displacement, is equal to 1/2 V naught plus V times time. And in straight line one-dimensional kinematics, this is basically just average velocity times time. So number 4, and again, this is the third one it doesn't appear on the AP equations sheet, but it is a very handy one to know. Now my fourth equation is going to come from a combination of number 1 equation and this area equation I just wrote out. So up in the top right, I've put equation number 1 up there again to remind us, and solved for T. Now that solution for T, which is just delta V over A, I'm actually going to substitute that value for T, in for the T variable from equation number 3. Let's see what that looks like. I get delta X equals 1/2 times V naught plus V times my substituted value for T, which is V minus V naught over A. I'm going to get that A and that 2 onto the other side of my equation. There it goes, 2A delta X. And then I get some FOIL time with V naught plus V times V minus V naught. We'll write that out just to see what it looks like. We see those values cancel. I got a positive and negative V times V naught. And I'm left with a minus V naught squared plus V squared. Move things around to make it look a little pretty, get rid of that minus sign, and we'll end up getting it the way that it appears on our AP equation sheet, namely that final velocity squared equals initial velocity squared plus twice the acceleration times the displacement of the particle. I often write it like this, as well as most everybody else. Okay, I'm going to copy over, rather oddly, the equations from previously, so we have all 4 of them written there. And we'll just do a very quick little problem and overview. Few things. I'm just going to read through 1, 2, 3, and 4 and say what they mean in English. We should be able to read an equation, its variables, in words. So, starting with number 1. The velocity, the final velocity of a particle, after some period of time. You define when you're looking at some phenomenon. You have a starting time and an ending time. And that's referred to as the initial or final. And with our subscripts, we sometimes say not for the initial and then just the regular symbol as the final. So number 1 says final velocity is equal to initial velocity plus acceleration times time. Number 2 says the final position of the particle is equal to the initial position of the particle plus its initial velocity times the time plus 1/2 times the acceleration of the particle times the time squared. So there, this time is corresponding to the amount of time it experiences some acceleration. All the t's in that equation would have to have the same value. All right, number 3 says delta x, or x minus x naught, so the change in position of the particle, is equal to 1/2 times the sum of the velocities, initial and final together, times the time. Number 4 says the final velocity of the particle squared is equal to the initial velocity of the particle squared plus twice the acceleration times the change in position. Now, depending on what variables you have 5 kinematic variables and 4 equations here. So there are actually only 3 equations printed on your AP equation sheet. So these are the 4 kind of all of them that we were taught originally back in the day. And so since you have 5 kinematic variables, your 2 velocities, acceleration, time, and displacement, if you have 3 of your kinematic variables known, then you can solve for the unknown one. You just have to pick which equation to use. So we'll do a quick problem in a momento, but final FYI for these are kinematic equations, meaning the equations that describe motion for uniformly accelerated motion. They don't work if your acceleration is constantly changing. So here's a little example problem. A car accelerates from 20 meters per second to 28 meters per second to pass another vehicle. The car has a constant acceleration of 4 meters per second squared. How long does it take to reach its final speed? So the first step is always, identify. Those are our 5 kinematic variables there. Let's identify what we know. I write on my problem, my question, and so identify my v naught is 20 meters per second. That's the initial velocity. Its final velocity, v, is 28 meters per second. I write that down in my little table of known stuff there. I have constant acceleration, so that tells us it's UAM, it's constant acceleration, and the value of 4 meters per second squared. It's important that I see my units are all consistent there. If my acceleration was 40 centimeters per second squared, I'm going to make sure we convert if necessary. And the question is asking how long does it take to reach its final speed, so I know I'm looking for time. So I put a little box around my t there. I know that's what I'm looking for first. Notice no mention of delta x. And so the next thing I'm going to have to do is find a relevant equation to use to solve this. And since I don't have any information about delta x or displacement, I'm probably not going to want to use an equation that involves delta x. So let's pick the first one. V final equals V initial plus AT. And so when I write that, I copy over my equation as it is. In this case, in this example, I'll go ahead and solve for t to make it easier on myself. So I solve for t because I've done literal equation practice. And I got 28 meters per second for final velocity minus the initial velocity of 20 over 4 gives me my time. Check our units there for dimensional and unit-specific analysis. You notice I end up with s there. That s squared cancels out with the single s on the bottom for my seconds, so I end up with not seconds squared but just plain seconds. My meters cancel out, so our units are good, our dimensions are good. And what value do we get? Looks like 2 seconds. Okay, so I can write that in for the value of my time. And now say we asked how far did it travel in that time. Okay, you found out how long it was accelerating for. How far did it travel, the car? So I'll pick equation number 2 to look at this one because I have, and I told you how I write it, I subtract x naught from both sides and I get that x final minus x initial, so that's delta x equals v naught t plus 1/2 at squared. Now I'm on the bottom left. Remember those are vectors, so just be mindful of the sign, positive or negative. They could be one or the other. If the car's braking while it's traveling in the positive direction and it turns the brakes on, that's the negative acceleration and it's going to start slowing down because when our velocity's direction is the opposite of our acceleration direction, that's when we have slowing down. When they're in the same direction, that's when we have speeding up. So notice using this equation, I can solve it. Check out my dimensions again. They check out okay. And I come up with the same answer, 48 meters. So my equations are consistent. I have also this equation, the one for my trapezoid. You can see that one real quick, that it's going to come out to 48 meters. And my final equation I can look at for consistency again. I'm going to solve for delta x, and I have v squared minus v initial squared over twice the acceleration. I have no idea what 28 squared is, 784 minus 400, and we're left with, again, 48 meters. So look at that, 3 consistent evaluations of what the displacement should be. These are our uniformly accelerated motion kinematic equations. We'll have lots of practice with them, study them, come with questions.